Hello, everyone, and welcome to our talk, A Beginner's Guide to SelectionDAG. A year ago, I attended the conference and wanted to contribute to the project. I started learning about NVPTX, and though it was kind of easy to learn about particular parts of the backend, putting together the big picture was really difficult. And so the purpose of this talk is to help someone that wants to learn about SelectionDAG or contribute to a backend get the full picture of what's going on, so that they can feel comfortable and confident as they contribute to a backend and the SelectionDAG framework itself. Now I'm going to hand it off to Alex to talk more about why SelectionDAG.
Hello, everyone. So as Justin said, we're going to be giving a high-level overview of SelectionDAG. For those of you who don't know, SelectionDAG is a framework for instruction selection. So that's the process by which we take LLVM IR and turn it into instructions that can actually be run on a real machine. So there's two main reasons why we thought it would be worth talking about SelectionDAG today. The first is that it's really important. Many targets use SelectionDAG for instruction selection, and the decisions made here can have a really big impact on the final code quality. So we can do well in optimizations, we can do well in machine instruction optimizations, but there are a lot of important decisions we need to make in SelectionDAG. And in addition, supporting any new target instructions or intrinsics requires SelectionDAG changes. The second reason it's worth talking about SelectionDAG is that it can be really confusing. It's sort of a weird thing because it's a tool for instruction selection, which is really target specific, but it's a generic framework. And this is accomplished with abstraction, which is really powerful, but also can be really confusing. So there's just a lot of code and a lot of different files, and it can be hard to tell what exactly is going on. We also use things like table gen, which are really powerful, but also introduce more complexity. So who is this talk for? We're going to assume throughout that you have some basic familiarity or comfort with LLVM. Maybe you've heard of SelectionDAG, maybe you've worked with it before, but you feel like you don't quite get it. If this is true of you, you are the perfect audience for this. So what we're going to talk about today is first we're just going to review how SelectionDAG fits into the overall compilation flow. Next, we're going to look at the SelectionDAG data structure. And after that, we're going to look at each of the main phases of SelectionDAG. At the end, we'll go through a quick example of working with a target, adding a feature to a target that uses SelectionDAG. Before we get started, a couple quick caveats. As you can probably tell by our youthful complexion, we're not the authors of this framework, nor are we experts in it. We've also primarily worked with NVPTX. This talk is intended to be general, but our experience with what we've worked on is probably going to inform what we find interesting. We both have around 2 years of experience with LLVM and NVPTX, and we've learned a lot in that time, and hopefully we can share some of that with you, but we are not experts. Another quick note is that there's an alternate framework for this called Global ICEL. That's not covered in this presentation, but just keep in mind that your target may not use SelectionDAG all the time.
So with that, where does SelectionDAG fit into our compilation flow? Here's our standard compilation flow diagram. Our front end parses the source code, generates LLVM IR, optimizes it, and LLC spits out assembly. SelectionDAG lives within LLC. In particular, it's between the LLVM IR passes, and machine IR passes. Let's look at what SelectionDAG's doing. Well, first, it's constructing the SelectionDAG data structure. Again, SelectionDAG is both a framework and a data structure. With our SelectionDAG, we legalize the types and operations to ensure that they're all supported by the target we're compiling for. We then perform instruction selection to select the particular machine instructions that will run on the chip and schedule them to go from a DAG of instructions to a linear sequence of machine IR. In between construction and our legalization phases, we also perform people optimizations with DAG Combiner. This is to eliminate any inefficiencies we could have introduced and our lowering and legalization. With that, Alex to talk about the data structure.
All right, so SelectionDAG is a framework, and it's also a data structure. Some of you may have guessed it's a directed acyclic graph. And this is a way to represent the meaning of our program. So it's an It's another form of IR similar to LLVM IR or machine IR. One important thing to keep in mind about these DAGs is that each one represents a single basic block. So during our construction, we're going to break our program up into basic blocks. We'll do all the phases of instruction selection on each DAG, and then we'll reassemble them at the end. So before we can get into the SelectionDAG data structure, let's take a quick digression into types in the SelectionDAG. There are two types that it's worth keeping in mind when talking about SelectionDAG. The first is machine value type. This is a set of types that's the union of types supported by each architecture. So any given target won't support all of these, but any element in this set is supported by some architecture. MVT includes integers, floats, vectors of both these types, as well as some other things. The other kind of type that is worth thinking about for SelectionDAG is the EVT. This is the extended value type, and this includes everything that's an MVT, plus non-standard sized integers and vectors that LLVM IR supports. So it includes things like I3 or V100 that aren't natively supported on any target. It doesn't include all LLVM IR types, so structs and arrays are not part of this set. All right, so now we're going to build the SelectionDAG for this little basic block. So we have this little piece of IR. It's 3 instructions. We're going to take some value A defined outside of the block. We're going to add a constant to it. We're going to take that result and multiply it by a constant, and then we're going to branch somewhere else. So we're going to go through the next few slides and build up what does the SelectionDAG look like for this block. So the first thing that we need to talk about is the SD node. These are the basic building blocks of all selections DAGs. Every SD node has an opcode, which defines what kind of node it is. It also has potentially many other fields. So coming back to our example, we're going to define SD nodes for every instruction. So there's an ISD add, mul, and branch node. And there are also going to be nodes for the constant values. So there's a constant 5, constant 3, and an ISD basic block for the address of the join. So here, with the constants in the basic block, you can see an example of another field in a node. These also have the value, so the 3, the 5, and the join. The next component of the SelectionDAG is the SD value. This is sort of the output of an SD node. It can be represented as an SD node that's producing the output and an index into the list of outputs. So unlike LLVM IR, in the SelectionDAG, any given node can produce multiple outputs. In this example so far, we're only seeing nodes with a single output, but later we'll see some where there are multiple. Each one of these SD values has an associated EVT. So in our example, the add, mul, and the constants all have the MVT I32 type. The branch and the basic block have MVT other type. The next component of the DAG is the SD use, and this is a way to represent the input to an SD node. It can be defined as an SD value and a node that's the user and an index into that node's operand list. These are the edges of our graph. So you can see in our example, we've created a use from the mul to the add. One thing that's important to keep in mind with all the diagrams here is that the arrows are representing uses, not data flow. So the arrow is going from the mul to the add, even though really the information is flowing from the add to the mul. So now if we go back to SD nodes, we can say a couple other things that they have. One is that every SD node has one or more result represented by an SD value. They also can have 0 or more operands represented by SD uses. So for example, the constants don't have any operands. All right, so as you can see, our graph is looking pretty complete. It looks like we've captured a lot of the meaning of our original IR, but there's still a few things missing. One of those is A and Z. So these are the values that are live across multiple blocks. And we need some way to represent these. The value Y, which is only defined within this block, it just kind of disappears. But we do need a way to capture the information about A and Z. So when we're reassembling all these blocks at the end, we'll know how to stitch it all back together. So for this, we're going to create copy to and copy from register nodes. This is a way to represent either a dependency on some value used in another block, or say that we're going to take a value and other blocks may depend upon it. These are a little bit like load and store instructions, not in that they have anything to do with memory, but just that they take some value and an address and either read to it or write from it. In this case, the address is an ISD register. So one other thing that we're going to need to add to this graph is, as you can see right now, I've pictured the branch below the mole, but the SelectionDAG doesn't have any inherent ordering. So there's no reason that the branch needs to be there. And when we're scheduling, right now, the way it's shown, there's no reason that the branch is not going to be the first instruction in the block. Obviously, we don't want this. So we need a way to represent dependencies that aren't data dependencies. And we're going to do this with chains. Chains are SD uses that don't represent actual data flow. They're not going to become a register. They just represent a dependency. And the nice thing about them is there's no really special handling of them. But when we're scheduling, we need to do a topological sort. And those chains will just ensure that that topological sort knows about these dependencies. So in this case, we're going to create a chain value from the branch to the copy to register. And this is saying that before we branch to some other basic block, we need to take the value computed by the mole and put it in this register. Throughout the slides, branches are going to be represented, throughout the slides, chains are going to be represented by this dashed blue arrow. So a couple more things to complete our SelectionDAG. One is the entry token. This is going to be part of every SelectionDAG, and it represents the start of the block. In this case, we're creating chains from the copy to and the copy from register to the entry token. And this is just a way to say that we don't want to do these things until we've entered the block. The other thing that every SelectionDAG is going to have is a root. Usually this is the terminator instruction. And certain transformations are going to start from this node. So with that, we have completely built the SelectionDAG for this little basic block. All right, let's look at one more quick example before we move on. This is a basic block that stores a constant and then loads a value to be used in some other block. As you can see, the SelectionDAG for this very small example is already getting quite big. I've grayed out a lot of the nodes that we've seen before that aren't really that interesting. Let's take a minute to talk a little bit about some of them. So the first is the load and the store node. And as you'll notice, the 0th operand of these is a chain. So the store is chained to the entry token, which just means that we don't want to do the store unless we enter this block. And the load is chained to the store. And this ensures that if the pointers that are loaded to and stored from end up being the same value, that in the final assembly, they're emitted in the correct order. You could also see that these load and store nodes are memory SD nodes. So they have a lot of additional information. That's represented by that second line there about what's going on, the alignment, stuff like that. One other node we should touch on here is the token factor. This is sort of a weird name, but really all it is a way to take two chains and join them together. So this is a way for the branch to depend on two different things happening. In this case, before we branch, we need to store a value, and we need to make sure the value from the load is copied to a register. So it's not going to become any instruction. It's just a convenience to allow a node to depend on multiple values. All right, so now that we've talked about the SelectionDAG data structure, it's time to go through the phases of SelectionDAG. And the first of which is building a SelectionDAG. So during this phase, we're going to build a representation of each basic block in the function as a SelectionDAG. For the most part, this is going to be largely one-to-one. So we're not going to do a lot of lowering to target-specific semantics. We're just going to take the LLVM IR values and produce the analogous SelectionDAG nodes. There are two main exceptions that we need to talk about, though. One is structure types. So structs are not supported in SelectionDAG. So these need to be lowered element-wise. The second is there are some instructions which are too target-specific for a generic implementation. And for those, every target is responsible for building their own target-specific set of nodes. So first, a little example with structs. In this block, we're going to load a struct and just extract a value. And as you can see, this has been lowered element-wise. So now there are two loads, one for each element in the struct, and we're offsetting the second load with an ISD add to ensure that it's it's loading the second element. There's also two nodes down below them that represent sort of the struct. So the first is merge values, which is just another convenience node. It's just going to take the values that it's passed in as operands and pass them through as returns. So this is just a way to represent values defined by multiple different nodes as values defined by a single node. It also doesn't correspond to any instruction, and it will be optimized out. The other is a token factor, and we've already touched on this. In this case, it's just providing a way to represent a dependency on loading the entire struct. Nothing depends on that in this case, so there's no uses of it, and it will also get optimized out, but in some cases that could be useful. So target-specific APIs. Some, as I mentioned earlier, some IR features don't have a generic SelectionDAG representation, and targets need to implement them themselves. So that is calling conventions. So lower call, lower formal args, and lower return. Every target needs to implement these in TLI and look at the IR and produce some SD value that represents that instruction. All right.
So at this point, we've lowered our LLVM IR into the SelectionDAG. But now we need to ensure that all of the types and operations are supported by the target we're compiling for. The first step of that is type legalization. Targets only support a subset of the types that LLVM IR supports. In the diagram, you can see that LLVM IR supports types like I24, V3I8, and I128. Whereas, in this example, PTX supports types like I32, I64, float, and double. During type legalization, we need to lower the illegal types to legal types. But what does legal mean? If we go back a slide, you can see that we perform legalization before instruction selection. When we say that a type or operation is legal, all we're saying is that our code in instruction selection can handle it. So how do targets control this behavior? SelectionDAG provides the addRegister class function. When a target calls this function and passes a particular MVT, that communicates to SelectionDAG that that MVT is legal for the target. Interestingly, given just the set of legal types, SelectionDAG can legalize all the unsupported types for us. Behind the scenes, it's constructing a table that maps every type to an action that will legalize that type. This table contains, or rather the table on the slide, contains the different legalization methods for the types in our program that SelectionDAG can use. We're going to look at a couple of these in the next few slides. First, expanding an integer. On the left, we have an I128, a type that, for this hypothetical target, is not supported. However, I64 is. So SelectionDAG legalizes our I128 add to I64 add carries. An important thing to note here is that even though we're in the type legalization phase, we aren't just touching the types. We're also making modifications to our DAG. Next, promoting an integer. On the left, we have an I24 add. I24 isn't supported for this hypothetical target, whereas I32 is. So SelectionDAG will promote our I24 add to an I32 add. It will also modify our zero extend and turn it into an AND that masks off any bits that could be set by performing our I24 add on an I32. Vectors can optionally get some special handling. If a target would like to, they can implement or override the getPreferredVector action function. SelectionDAG will call this and provide a type. When targets override this, they say, for this type, what legalization action should be performed to legalize that vector type. When Hexagon encounters a V3I8, it utilizes this method to override SelectionDAG's behavior and ask it to widen our V3I8 to a V4I8, even though it takes some more space. So I hope that gives a brief overview of how we take a DAG of any type and turn it into a DAG of types that our instruction selection code can handle. But now we have our operations to handle. SelectionDAG supports over 400 opcodes. For one, targets don't support all of these opcodes, but additionally, they don't support any one opcode for all legal types. Our goal in this stage is to lower all operations that are supported by SelectionDAG to operations that are legal for the target. How do targets control this? SelectionDAG provides the setOperationAction function. Targets call this function for a particular opcode in MVT and communicate to SelectionDAG what legalization action should be performed for that opcode in MVT. An important side note, the semantics of the NVT parameter aren't well defined. Sometimes it's the operand type, sometimes it's the return type. When in doubt, it's always safest to just read the code. Behind the scenes, SelectionDAG is constructing a table that maps every opcode in legal MVT to an action that will legalize that opcode in legal MVT. SetOperationAction is how targets override the default values in this table that SelectionDAG sets. Below, we have some of the legalization actions that targets can specify. Legal just says, you don't need to touch this. Our instruction selection code can handle it, and it's all good. In the next couple slides, we'll look at promote, expand, and custom. In NVPTX, we support FP16 types, FP32 types, and FP32 division, but not FP16 division. Our solution is to execute FP16 division on the larger FP32 type. We do this by calling setOperationAction for floating point division, specifying FP16, and asking SelectionDAG to promote it for us. Here, we can see the input and output DAGs of our setOperationAction call. Our floating point division gets promoted to an FP32, and SelectionDAG inserts the necessary extends and rounds to ensure we're properly respecting the semantics of our original DAG. Next, expand. MIPS does not support the byte swap operation on I32. Byte swap is just reversing the bytes in a particular value. Our solution here is to ask SelectionDAG to emulate the byte swap operation with a DAG of operations that are legal for the target. We do this by calling setOperationAction for byte swap I32 and asking SelectionDAG to expand it. An important side note, expand does not specify how we emulate the operation. It's just requesting SelectionDAG to put in another DAG of legal nodes that properly emulate it. Here's our before and after. Our byte swap gets transformed into a DAG of ands, shifts, and ors that properly emulate the byte swap. What if promotion and expansion aren't enough for our use case? That's where custom legalization comes in. We can call setOperationAction for an opcode in MVT, specify custom, and that tells SelectionDAG that we want to implement a custom lowering for that opcode in MVT. When SelectionDAG encounters that opcode in MVT, it will call the lower operation function. And targets can override lower operation to implement their custom lowering. In NVPTX, we could ask SelectionDAG to expand the vector shuffle operation. But as a compiler engineer, we know that our PTX ISA that we're targeting supports the permute instruction. And the permute, the semantics of the permute map really well to the vector shuffle operation. So I'm going to implement a custom lowering to take our vector shuffle and produce a permute. SelectionDAG couldn't do this for us because it doesn't know about these target-specific nodes. It only knows about the nodes that are generic and supported by SelectionDAG and all targets. Our next example is from x86. x86 chooses to implement a custom lowering for absolute value. They lower it to the x86 specific subtract and conditional move instruction. Subtract returns a flag that indicates whether the input was positive or negative, and we can use that in our conditional move operation to determine whether to return our original input or the result of the subtract. Okay, with that, we've legalized the types and operations in our DAG, and we're now ready to perform instruction selection. But before we do that, let's look at DAG Combiner. DAG Combiner is how we perform peepholes on our selection DAG. But you might be asking, why are we doing this in the first place? Haven't we already implemented all our peephole optimizations in LLVM IR? Well, for one, we want to clean up any inefficiencies we introduced while lowering into the selection DAG and legalizing it. We also want to generate unique operations that are provided by our ISA that might be faster than the set of default operations that SelectionDAG gives us. So first, let's talk about DAG Combiner. DAG Combiner performs peepholes for all targets that use SelectionDAG. It's essentially the ins combine for SelectionDAG. SelectionDAG calls target lowering info to understand which optimizations are profitable for a particular target. Below, we can see a code snippet from DAG Combiner. Before performing the DAG combine and returning the optimized code, it calls TLI to check whether the negated expression will actually be cheaper. If it is, we perform our operation and take our add and fneg and produce a floating point subtract. If not, we don't touch it. But what if the optimizations we get for free from DAG Combiner aren't enough? Well, we have custom DAG combines. We communicate to SelectionDAG that we want to implement a custom DAG combine by calling setTargetDAGCombine and passing an opcode. When SelectionDAG sees that opcode, it will call performDAGCombine. Targets override performDAGCombine to implement their optimization. Our first example is from NVPTX. On the left-hand side, we have a multiply. This multiply requires 128 bits for to store the operands. In PTX, we care a lot about register pressure. So we have the mul-wide instruction. Mul-wide can take in two I32s and produce an I64. So, as compiler engineers, we implement a custom DAG combine that examines our I64 mul to determine if the inputs are using the high 32 bits. In this case, it's relatively simple to see that our 0 extends mean that we aren't using those bits, and so we can successfully transform it into a mul-wide by inserting truncates to make sure everything fits. But you might be saying, we might have addressed our register pressure issue, but we've also introduced more instructions. Is this actually better? Well, luckily, similar to ins combine, DAG combine runs iteratively. It will identify the redundant 0, extend, and truncate and produce our DAG on the right that both has fewer instructions than our original DAG and less register pressure. Our next example is about unsigned remainder. Unsigned remainder is a very expensive operation in PTX. So as a result, we prefer to implement a custom DAG combine that lowers our DAG on the left to a DAG that utilizes multiply and subtract, the result of the division, and a multiply and subtract to emulate our unsigned remainder operation. The takeaway here is that even though we aren't generating a target-specific node, we're utilizing information that, as compiler engineers, we know about our target to make the best decision. Now, Alex will talk about instruction selection.
All right, so now that we have legalized and to some extent optimized our DAG, it's time for instruction selection. So during instruction selection, we're going to replace most of the generic SD nodes with machine nodes. And machine nodes are just like normal SD nodes, except that their opcode is a machine instruction opcode. So they directly correspond to some machine instruction. Unfortunately, this is too target specific for a generic implementation. So for all the previous stages, we maybe implemented some callbacks or we filled out a table, and then SelectionDAG took it from there and did most of the work for us. That's not the case for select. So as you can see below, this is the implementation of select that SelectionDAG provides. There isn't one. So each target is going to need to override this method and implement a lot of matching code to perform selection, to convert all the generic nodes into target-specific nodes. And if that sounds like a lot of work, there is a solution. So TableGen allows us to succinctly specify these rewriting patterns, and then it will write all that nasty C++ code for us. And we just get to write some more simple, abstract definitions. Targets can still implement this logic themselves for certain opcodes outside of TableGen as needed. So how do we get TableGen to do this for us? There are three main things that we're going to need to define for TableGen. The first is SD pattern operators, and this is a way to describe what we're looking for in the DAG. The second is instructions. These are the representations of machine instructions which we want to emit. And then the last is patterns, which map these two things together. We're going to look at all three of these for a really simple example, which is lowering the add instruction on NVPTX. So first, let's look at matching the selection DAG. Here we need to define what we're looking for in the selection DAG. So first thing what we're going to do is define a type profile. This is just a description of what the type of our node is going to be. So for the add, we say it's going to produce one value and take two operands. We also say that the operands are all going to be the same type of integer. The next thing that we're going to define is an SD node. And this is a subclass of SD pattern operator. And here we're going to say what opcode we're expecting it to have, so ISD add. We're going to use the type profile from above. And we're also going to assign it some additional properties. So here, commutative and associative. And this just gives TableGen more flexibility when it's generating the matching code for us. So if it sees that some pattern matches on the DAG, if we commute the operands, it will automatically do that for us. All right, so now that we've defined what we can look for in the selection DAG, we need to define a machine instruction that we're going to produce. TableGen lets us populate machine instruction entries with a lot of useful information that can be used in many different places, such as the assembly printer or the machine IR transformation passes. For SelectionDAG, there are really three key pieces of information that we need to care about. The first is the opcode name for this instruction. So in this case, that's add I32RR. This is going to go into a big enum, and it's going to become the opcode of our SD node. The next thing that we care about is the outs, and that is a definition of what's going to be produced by our node. The last thing that we're interested in is the ins, and this is just a definition of the inputs that this instruction takes. You can see here there's also an assembly string, which will be used by the assembly printer, but for SelectionDAG, we don't care what that is. So now that we've defined this add SD pattern operator, and we defined this add I32RR instruction, we need to tell SelectionDAG how they correspond to each other. And we're going to do that with a pattern. So a pattern takes two operands, each of which is a DAG represented in this sort of S expression language. And it's first we're defining what we're looking for, and then we define what we're going to turn it into. So here we say we're looking for an add that's producing some I32 register, and it's taking two I32 registers as input. And for that, we're going to produce this add I32RR instruction with those same inputs and output. And with that, we've given TableGen all the information it needs to perform the following transformation during instruction selection. So now TableGen knows to look for this add of these types, and when it sees it, it knows to convert it to this add PTX instruction with those same inputs. So back to this select method, which we need to implement. Here is how most targets do it. So the first thing that we can do is implement any custom logic we want. So we're going to be given a node, and if we don't want to use TableGen for some reason, maybe this node is really complex and we just haven't figured out how to represent that transformation in TableGen, or maybe for legacy reasons, the code's just there, we can implement that first. Then we'll call select code, which will throw to the TableGen generated matcher. And this is a big illegible switch case that will perform the TableGen-based transformations for us. So a couple important notes about the SelectionDAG algorithm. The first is that the DAG is traversed in bottom-up order. That means we're going to start with the instructions that are later in the graph and move towards the entry token. What this ensures is that an operator is always going to be selected before any of its operands. And this allows us to match on a node and properties about its operands, and we can guarantee that those operands are also going to still be in the generic form. They won't be selected yet. One other thing to quickly touch on is how TableGen prioritizes matches. So often there may be cases where multiple different patterns match on a given DAG. And this can be because we have patterns for more complex cases and simpler cases. So the first thing that we're going to do is we prefer the more complex match patterns. So if there's a match that's looking for a really sort of large DAG with lots of different operand constraints, we'll prefer that over a more simple case. When there's a tie there, we fall back to a lower emitted instruction count, which is a proxy for cost. If that is also a tie, we'll fall back to the match pattern size. And finally, we prefer later source code order. So we could spend a whole hour just talking about TableGen. There's a lot that we haven't been able to get into just because of the time constraint. But for the most part, almost every selection that we want to do can be represented in TableGen pretty efficiently.
So next is instruction selection. Our input to instruction selection is a DAG of machine nodes. Scheduling, sorry. And our output is a linear sequence of these machine nodes. We could just perform a simple topological sort. In the case of PTX, the code we generate is the input to another compiler that actually schedules the instructions that are run in the chip. And as a result, for the NVPTX backend, we don't rely heavily on this. Since we don't work with it, we don't really know what we're talking about, we aren't going to tell you about it. Instead, check out this blog post and this developer meeting talk if you're interested in learning more. Now for an example of working with SelectionDAG. So, our example is going to be about the PTX MAD instruction. MAD takes in two values, multiplies them, and adds a third. Our goal is to emit the PTX MAD instruction via a people optimization. Why do we want to do this? Well, our MAD instruction will have lower latency than a multiply followed by an add, and it will could reduce register pressure. First, what don't we need to do? MAD only supports existing legal types in NVPTX, so we don't need to touch type legalization. Additionally, the nodes we want to match on, adds and multiplies, are already legal for all the types that the PTX MAD instruction supports, and so we don't need to worry about operation legalization. One side note, we're just going to look at I32 for this case to reduce the amount of text on the slide. What do we need to do? Well, for one, we need a target-specific DAG combine to generate our target-specific SD node, NVPTX ISD, IMAD. We then need instruction selection logic to lower our target-specific SD node into a machine node. So step one, our DAG combine. We want to take our add that takes in a multiply on the left and generate our IMAD. Our first step is to declare to SelectionDAG that we want to implement a custom DAG combine. We do this by calling setTargetDAG combine and specifying add. We then implement or override the perform DAG combine function. Additionally, we add a case for the add opcode to call our perform add combine function, the function we're actually going to perform the people in. In perform add combine, we first do a couple checks and then actually implement the fold. Our first check is that the operand is, one of the operands is a multiply. If it isn't, it's not the pattern we're looking for and we don't want to touch it. We also check that it's of the correct type. If this is an I7 add, we don't want to generate an I7 IMAD. And finally, we check that our multiply only has one use, to not extend its live range and increase register pressure. Once those checks have all passed, we can then generate our target-specific SD node. We specify its opcode, NVPTX ISD IMAD, its type, its first two inputs, which are the operands of the multiply, and the last, which is the other operand of the add. By returning this node that we've created, we ask SelectionDAG to replace the node that it's passed us, the add node, with the node that we've generated. It will also eliminate any dead nodes that this DAG combine could have introduced. So we've taken our add and multiply and produced our IMAD. Now we need to perform instruction selection and lower our IMAD target-specific SD node into a machine node. So step one, we need to tell SelectionDAG what to look for. The type of our IMAD node is defined above at the very top of the slide. One output, three inputs, all of which are ints. Our IMAD SD node has the NVPTX ISD IMAD opcode and the type that we define above. The instruction we want to generate is a MAD I32 RRR. We create this machine instruction, our NVPTX instruction, say it has one I32 output and three I32 inputs, and specify the assembly string that this will result in. With the SD node table gen should look for, and the machine instruction it should generate, we can write a pattern that looks for the SD node and generates the machine node MAD I32. And with this, we've taken our IMAD and produced our machine node, the MAD I32. So we implemented a DAG combine to take our LLVM IR that got lowered into SelectionDAG, take our SelectionDAG mul and add SD nodes to produce our target-specific SD node, lower that target-specific SD node to a machine node, which then generates the assembly on the right, the mad.low S32. So some final notes. We hope that all of this helps people in the audience, people watching on YouTube, to feel more confident and comfortable working with SelectionDAG. And we hope that people will start to contribute to backends and the framework itself. To jumpstart this process, these are a few of the resources that Alex and I used as we were getting started. Highly encourage you guys to use them as well. There are also links throughout the slides to relevant sections of the code base. And we also recommend learning the output of debug only equals icell and these other things you can pass to it. This is a really useful thing to use when you're debugging SelectionDAG and trying to understand what's going on in each of the phases. And a final thank you to Akshay, Max, Drew, Vlad, Kevin, and Princeton, whose name isn't on the slide. And that's all. Yeah, thank you for the time.
Thank you, Alex and Justin. If you have any questions, make your way to the aisle or raise your hand. I'll pass you the mic.
So just one final note, it was actually the wrong slide deck. So this is the link to the slides. If you want to download it and check out the links and stuff, feel free to use that. Yeah.
Hi, this is a question born of deepest frustration. How does one learn the details of the semantics of TableGen's matching or pattern matching syntax? I have tried to do this maybe a dozen times over the last 2 years and have failed every time. So you seem to have been successful at this. Is it written down anywhere?
Not that we know of. Trial and error would be how we learned it. I'm sure we just haven't found the documentation and it's out there somewhere. But this is not something we. Yeah.
Thanks.
Sorry, don't have a better answer.
Any more questions?
So these DAG combined patterns or DAG combined code, can that be written as patterns in selection in TableGen for DAG combines? Can they be expressed as patterns?
No, DAG combine is only imposed. So the question was, can DAG combined patterns be defined in TableGen? And the answer is no, not that I know of.
Thank you so much for this talk. Tremendous resource. I'm so glad it's recorded. Hi, Mom. It'd be useful to share with colleagues in the future. Just got a SelectionDAG joke for you. Why does my editor crash every time I open x86 SelectionDAG, DAG to DAG? I saw lowering. Yeah, there's no punchline. I just Craig and Simon, if you're here too. Oh, right. Okay. Thanks.
Hey, thank you for the talk. I'm just wondering, how do you compare the code gen quality with the global ICL? Do you have any experience with that?
We have no experience with that.
Thank you for the talk. Yeah, so the DAG has a lot of combiners and all that. I'm just making a comment, and it's a long effort for global ISL to catch up. So there's something called a SelectionDAG compat.td, which basically allows you to import all the patterns to the global ISL world. So that's sort of a compatibility layer where you can do that. And in terms of the performance, global ISL is not there yet because it is not function complete. A lot of things are going back to the SelectionDAG. The entire machine function will get reset through the machine property, and it will try to do the selection again. So that's how the global ISL is still using the SelectionDAG. So I just wanted to pass that on. Thank you. Thank you for the talk.
Thank you.
Thank you for the talk. On one of the slides, you showed a custom lowering of vector shuffle to NVPTX permute instruction. And I believe you can also do that in TableGen. So what determines the approach you take?
Yeah, this is an interesting point. So in general, anything that's being done during operation legalization, we can also just pass those operations through and handle them in instruction selection. So it's sort of a matter of discretion where we want to handle them. So in this case, it just ended up being a lot easier to implement that as a DAG combine. For example, you can see that there's this constant node that we're adding, which is like a packed representation of the vector shuffle that we want to do. And it's just much easier to implement that as a DAG combine as opposed to as in TableGen.
I don't think TableGen can process. I don't think there's any TableGen syntax to process the mask for a vector shuffle.
Yeah, so it would not even be possible in this case.
Thank you for the excellent talk. Are the side effects, like the flags, considered like input-output, or is it different logic?
So side effects are represented as chains as far as I know. So yeah, that will ensure that side effecting instructions are scheduled appropriately. Does that answer your question?
Carry bit and those actually get into the logic. It's not just ordering. It's also part of the logic.
Carry bit is, on some targets, carry bit is an explicit output. On some targets, it is done through glue. That is the glue. That case there is using glue for the flag. On some targets, flags are explicit. x86 has an I32 output for the flags. For some targets, it's done through a glue operand, which historically was called flag and was renamed to glue at some point.
More questions?
Serious question this time. How do you recommend testing the individual phases of SelectionDAG?
I mean, I don't think we have anything unique to add here. MVPTX just runs LLC and checks the output. Yeah, not something I've thought about a lot. Yeah. Do you have anything more?
If one is playing around with SelectionDAG and wants to look at DAGs, what in your experience is the best way to do that? Like, is it a graphical representation, or like, is there a textual way to look at this that's more convenient? Like, how do you do it?
Like what Alex and I do when we're actually working with it is use the debug only equals iCell output, just because it's fast and we work on remote machines. So generating a PNG that you then have to switch over and stuff is a bit complicated.
And also, all these DAGs that we've shown you are like one instruction. For any real basic block, it's just unmanageably large. So we use the textual output. And that's what we recommend.
Any more questions? All right, thanks to speakers, Alex and Justin.
Well,